In this podcast, we're going to look at some IMFs, also known as intermolecular forces, and we're going to talk about how they affect liquids and solids. But first, let's just do a little intermolecular forces. All right, last chapter we talked about gases, and those are particles that do not attract one another very much. And in this chapter, we're going to talk about particles that do attract each other. The attraction between particles is what allows us for the formation of solids and liquids. So here you can see a couple different examples of some interactions that are occurring that we started learning about in class today. Basically, the whole point of this is that if you know what is in your compound and you know what type of forces are going on in your compound, you can explain the chemical and physical properties that are exhibited by that material. So all of these properties are going to depend on the spacing of the particles and the attraction among them. Solids can be ordered or disordered. They can be crystalline, where the particles are arranged in a regular 3D structure like you see here in SiO2, which is quartz. Or they can be amorphous, where particles do not have a regular orderly arrangement like this, and this would be an FiO2, so same compound, but in this one it is ordered crystalline, and this one it is not. So that's the difference between quartz and glass. Alright, we already know that motion in solids is very limited. Particles cannot undergo any translation with respect to each other. That means they cannot slide past each other. They vibrate in place. And the interparticle interactions and the ability to pack all the particles together so tightly is what gives us the structure of our solids. All right, so let's talk a little bit about IMFs. So intermolecular forces of attraction, those are called IMFs. Oh no, I have something popping up. Okay, it's still going. All right, intramolecular forces, that'd be INTRA, are the bonds that we've been talking about. So covalent bonds, ionic bonds, metallic bonds, those are intramolecular forces. Now we're talking about intermolecular forces, which are between two compounds. Okay, so the compound is made, it's got its intramolecular forces holding it together. Now we're going to talk about intermolecular forces, which are going to help us pack our solids and liquids close to one another. All right, there are four different types of solids. We have molecular solids, we have metals, we have ionic solids, and we have covalent network solids. Okay, and you see that these represent the different types of bonding as well as some intermolecular forces stuff. All right, so let's start talking about these IMFs. First off, each intermolecular force is going to involve some sort of positive and negative attraction. So Coulomb's law still applies here. Here's our list of intermolecular forces from weakest to strongest. Okay, so we have London dispersion forces, dipole-dipole interactions, hydrogen bonding, which is actually a subset of dipole-dipole, but is a super strong type of dipole-dipole. And then we have ion-ion, which is the strongest intermolecular force. All right, in ion-ion, we have a positive and a negative. So here you see a positive sodium and a negative chlorine, and they're going to align themselves so that chlorine, the negative, is always touching other positives, and the positive sodium is always touching other negatives. Okay, and we can measure the energy of this lattice structure, and that's called the lattice energy. It actually tells us the strength of that interaction. All right, the next type of intermolecular force is called a dipole-dipole interaction. It's the same idea as ion-ion, except now instead of dealing with ions, which have full charges, now we are dealing with Alright, so here we're just dealing with polar molecules instead of ions like the ion-ion interaction had. So now we have polar molecules. They're going to have partial positive and partial negative charges. So you have the hydrogen and the chlorine. Chlorine's going to give us our partial negative. Hydrogen's going to give us our partial positive on this polar molecule, and so the partial negative part of one molecule is attracted to the partial positive part of the other. So they'll align themselves just like an ion-ion interaction, except now we're dealing with partial charges in a polar molecule. So this interaction is not going to be nearly as strong as an ion-ion interaction. The dipole forces obviously result from the attraction between the positive and negative ends of polar molecules. And in an attempt to minimize the repulsion between the like charges and maximize the attraction between the opposite charges, they are going to fit themselves so that they line up such. So here you have partial negative, partial positive, so they are attracted to one another. And then you have the same thing. They can even stack on top of each other, like in a solid. You could have a partial negative, partial positive. And of course, dipoles are weaker than ionic or covalent bonds. All right, here's a different picture. Still have a partial negative and a partial positive, and you see the attraction there. All right, here is a different molecule. So they can stack on one another. So you have partial negative, partial positive, and then you see that they can stack in such a manner. And then water. Water is, of course, the ultimate example of a partial negative, partial positive. So they still align each other. Here's your partial positive and your partial negative on a water molecule. All right, here's a different look at it. This one actually shows more of the stacking that can occur between the partial negatives and partial positives. So same type of thing as ion-ion. All right, now you can have an dipole-induced dipole where you have a dipole molecule, a polar molecule that comes near a nonpolar molecule, and it can actually induce a charge on the nonpolar molecule. So it can cause the electron cloud to shift. So you see in this picture you have a cation that's positively charged. He comes near a neutrally charged atom, and you actually see the electron cloud come more towards the side where the cation is, because positives and negatives attract. And then you have a partial positive on here. But we have induced this dipole because we have brought something positive near it. Same thing can happen with polar. So here's a polar molecule, partial negative, partial positive. Bring it near a neutral molecule, nonpolar, and you see an induced dipole in it. The strength of the induced dipole is going to increase with the magnitude of the dipole on the polar molecule. So basically, the more polar the molecule, the bigger difference in electronegativity, the more easily it will induce a dipole on a nonpolar molecule. And a nonpolar molecule that is very polarizable, meaning it has a lot of electrons, a lot of excess electrons, so big atoms, tend to induce dipoles much more easily. All right, here's another example. We see this water molecule coming near a CO2 or a O2 molecule, that is neutral. It approaches with its partial negative, and you see a partial positive induced on this side and a partial negative induced on that side. All right, interactions between polar molecules are typically greater than between nonpolar molecules of comparable size because these interactions act in addition to London dispersion forces. So polar molecules have the ability to dipole-dipole. They're always going to dipole-dipole because they already have a partial charge. Nonpolar molecules, on the other hand, are going to be less likely unless they are near a polar molecule or an ion. Okay, so they have to have that present to have an induced dipole attraction. Ionic interactions with dipoles are very important because of the solubility of ionic compounds in polar solvents. Okay, so polar solvent means water, and then ionic interactions or ionic compounds are going to be any salt, any ionic bonds that you put in water. When you throw an ionic salt in water, like you see here, the water molecules will go around the sodium and chlorine, or the positive, negative, cation, anion charges, and align so that their partial negative and partial positives line up. So here you have a sodium. Oxygen is partially negative, so you see that all the oxygens are facing the sodium. Okay, so opposite charges attract. You have the opposite effect over here. You have a chlorine, which is a negative, and all of the partial positive hydrogen ions are approaching it. Okay. All right, here's a different picture of it. So here we have chlorine, water molecules, H's, sodium, oxygens, because they have all the extra electrons. All right, and here you see the water breaking off, and then you see hydration shells or water molecules surrounding it, and they're orienting such that the positives are going towards the negative ion, and the negative ends of the water molecule are going towards the positive ion. All right, hydrogen bonding is a special case of dipole-dipole interaction. It's about 10 times stronger than a usual dipole-dipole, but you have to have hydrogen-oxygen, hydrogen-fluorine, or hydrogen-nitrogen in your molecule in order to have a hydrogen bond. Okay, so you have to have a hydrogen, and then you have to have an oxygen, a fluorine, or a nitrogen. This works because these atoms are all very small and electronegative. A very polar bond leads to stronger intermolecular forces. All right, here we see some hydrogen bonding in water. So we see that it lines up, makes kind of like a crystalline lattice. And then here you see a big picture of hydrogen bonding. All right, the last force we're going to talk about is London dispersion forces. They are actually attractive forces that are between all atoms and molecules. So everybody does this. And it is very, very important when we're talking about big, large molecules like proteins and polymers and stuff like that. So biology really cares about London dispersion forces. Basically what happens is you have an instantaneous dipole where there's an uneven distribution of the electrons around the nucleus in a molecule. So you'll get all the electrons piled up on one side of the molecule, like there and like there. This makes a temporary partial negative and partial positive charge. Okay, so all of them can do this, and this accounts for most of the interactions that we see. All right, here's a different picture of it. Again, we're just having a distortion of the electron cloud. And then you see that they can line up. So here you have a distortion, positive, negative, and they line up just like an ion-ion or a dipole-dipole would. Every atom attracts every other atom with this force, even if hydrogen bonding is present or dipole-dipole is present. So everybody can do this. Here, still positive, negative, but the polarity is only temporary. So the distortion is just temporary. And then the more polarizable an electron cloud, the more the London dispersion forces can affect the molecule. So we're looking for lots of electrons, and large atoms or long molecules can easily polarize. Dispersion forces increase with the contact area between the molecules and with increasing polarizability of the molecules. So the more pi bonding you have, the more electrons you have, the more polarizable you are. Okay, pi bonding is especially important with this as well. All right, here's a couple examples to recognize. Ion-ion always occurs with ionic salts. London dispersion forces are always nonpolar molecules and every other molecule as well. Dipole-dipole interactions are just polar molecules. Dipole-induced dipole, you need a polar molecule to induce a temporary dipole on a nonpolar molecule. And then hydrogen bonding is a special subset of dipole-dipole where polar molecules that have hydrogen oxygen, hydrogen nitrogen, or hydrogen fluorine can bond. All right, thought you might like this little joke. Here you see that the boys in the class are very attracted to the girls outside. All right, and here's a nice little chart. I liked this chart because it kind of sums it all up. It tells us that ionic bonding is the strongest, covalent is the next strongest, then we have metallic, then we have ion-dipole, hydrogen bonding, dipole-dipole, ion-induced dipole, dipole-induced dipole, and London dispersion. So these are all the types of molecular forces that you can have.